Hello, and welcome to the lecture for Chapter 7 from the Cosmic Perspective, ninth edition. In this chapter, we're going to turn our attention to the solar system as a whole. In the previous 6 chapters, we've established some of the background of astronomy, and now we're getting into the specifics. So, let's talk about our home, the solar system, consisting of 8 planets and 1 star. Well, here's our planet in a way that you typically don't see it. Maybe you're used to obviously seeing lots of planets on the surface of Earth, but the pictures of Earth from space show the continents and cloud cover. But this one here is taken at such a vast distance that it is barely more than a single pixel with a slight shading of blue, perhaps reflecting some of that blue light, more than other shades, but arguably white as well, with some artifact of the lens taken by Voyager, which is a space probe that was built in the 1970s. So obviously this is a very old type of camera here. And what we're looking at is just such a vast distance on the very edge of the solar system, beyond the orbit of the last of the planets, beyond the orbit of Neptune, beyond the orbit of Pluto, well out into a region of the solar system called the Kuiper Belt. Looking back towards Earth, what we see is just a tiny little dot. In the vastness of space, a vacuum of radiation and no air. So that's our home, a little tiny pebble of life with a small protective atmosphere, which is important for perspective. And now let's talk about some interesting stuff with the solar system. So in the first section, which will be covered in this video, we're going to talk about the solar system as a whole, which of course is a very broad topic, and we'll spend more chapters getting into it in more detail. What are our goals in this first section? Well, first of all, what does it look like? Let's cover the basics, make sure we know the structure of it, where things are located, and some relative distances. And what can we learn by comparing the planets to one another? So if you just learn about each planet in a vacuum, so to speak, then you have nothing really to base it on. You might know a list of facts about that planet, but what does that really tell you in a broader scope? Well, you compare it to other planets. You can look for trends, which we'll discuss in the next section in 7.2, where we discuss patterns in the solar system. But here, we're just going to discuss the general idea of comparing planets and what are the criteria that we might compare between them. So here it is. Here is the solar system in a rather detailed and quite interesting figure. There's a lot going on here. I would definitely recommend or suggest checking out this figure in your textbook or in a set of slides in some detail, spending some time with it, reading over the notes, looking at the information, because there's really so much here. It's quite beautiful. So let's zoom in a bit, look at our own home. All right, so if we zoom in towards Earth and the terrestrial planets, we see that they're showing very crowded in. And the reason for that is because the orbits are shown to scale. All of the orbits here are showing their shape, so that whether they're elliptic or not, although they're all quite circular, and we have a certain 3D perspective here. But most importantly, we're seeing their relative radii. So let's just show one for example. So from the distance of the center of the sun to the orbit of Earth is this arrow, would be the radius, and then the distance from the center of the sun to the orbit of, say, Saturn is this value here. So what's important about that is we see that it's much further to Saturn than it is to Earth from the sun. Saturn is much further from the sun than we are. And by a factor of, obviously, by looking at it, maybe, I don't know, I mean, I do it, going backwards. If we compare more directly, you can see it's the comparison of this line here, right? That's quite a bit longer, 20 times longer. Well, if we think of the way we measure distance from the center of the star, how we kind of quantify distances in our solar system, we round them to what are called AU, which is an astronomical unit and represents Earth's average distance from the sun. So, well, then we look at Saturn, it might be 20 AU from the sun, 20 times further than the sun than us. Okay? So that's a really big gap, considering that all the terrestrial planets, so planets unlike Saturn and Jupiter, they're all crowded in. Earth, Mercury, Mars, Venus, they're quite close to each other, especially in comparison to the distances way out to the first of the gas giants, Jupiter, and the distances between all the gas giants themselves, which are much more spread out. So there's these two really defining features of the solar system. Terrestrial planets crowded in near the sun, and giant gas planets much further out and much further spread apart from one another. So interestingly, beyond that, we see that there's size comparisons in this figure. Now, the sizes are not on the same scale as the radii, because that would, of course, imply that Jupiter is many times bigger than the Sun. Instead, the size relative scales are set, on some much magnified version, but they still show the relative size between the planets. For example, the gas giants are indeed giants. If we look at the size of Jupiter or Saturn, we see their vast size relative to the terrestrial planets like Earth, or even Mars, which is smaller, and Mercury, which is barely even visible. It's just a dot in the picture. Now, those are key characteristics right there that would really be discussed and will be discussed more in the next section in terms of the overall pattern, the overall structure of the solar system. But we do see the 8 planets and a way to group them together. Furthermore, there is an asteroid belt that neatly divides the region of the solar system with the terrestrial planets and the region of the solar system with the giants, the gas giants. Beyond that, we can look at further information, which I won't get into here, talking about a list of details, so a good summary comparing the 2 categories of planets, a further zoomed out image showing the distributions of asteroids and comets in 3 distinct parts of the solar system called the asteroid belt, already mentioned, the Kuiper belt, and the Oort cloud. The asteroid belt includes asteroids. That's where the vast majority, not all, but the vast majority of asteroids in the solar system are found. The Kuiper belt and Oort cloud both include comets with some different characteristics, but all comets, which are distinct from asteroids and are a topic that we will discuss in some detail later. This last little part of the figure shows some top-down views of the solar system, both showing the orbits of the planets that are terrestrial and close in, zoomed, and showing some relative motion of the planets, showing that all planets, with the exception of Venus, orbit and rotate in the same direction. So we see there's very much a uniform direction in the solar system, an idea that's closely tied in with conservation of angular momentum and is something that we see throughout systems, movement in galaxies and in our own galaxy and other, like I said, star systems, nebula, and so on. The idea is that everything ends up rotating in the same direction, but certainly an exception to the rule, Venus rotates the opposite direction. So instead of orbiting and rotating counterclockwise like every other planet in the solar system, Venus orbits counterclockwise, so it maintains that part of the pattern, but it actually rotates on its own axis clockwise, which is called retrograde, and it's the only planet that does that. Now, it's thought to be that Venus is upside down. So the planet at some point would have rotated like everything else in the system, which is to say counterclockwise as viewed from above the ecliptic plane, because that's what this figure represents, a bird's eye view looking directly down on the solar system called the ecliptic plane, where the planets orbit. Well, Venus is upside down, knocked over somehow. And as far as that idea of knocked over, we see it on a lesser extent with Uranus that doesn't orbit upside down and has a little bit of, you might say, normal orbit, so counterclockwise, but it's almost completely knocked on its side. So it's more like 90 degrees, but just under, right, which we can see over here, right, our knocked over planet, Uranus. Why do we bring up these little interesting bits of trivia? Because this is a good way, besides looking at the planets and the rules to compare them and the overall structure, it's interesting to think about the exceptions, the weird little quirks of the solar system, the interesting, fascinating oddities, because sometimes the exception in its interest is part of what makes the rule interesting as well. Now, let's get into all those details of the solar system. Okay, so there's 8 planets, all right? There are not 9. Pluto is not a planet, okay? We can call them major planets. We can call them planets. Those are interchangeable terms. There are 8 of them. Now, beyond the planets, there's also dwarf planets. Dwarf planets are a separate type of object. They are not planets. They include Pluto. They also include Ceres, which is in the asteroid belt. It is an asteroid and a dwarf planet. Pluto is considered a Kuiper belt object and a dwarf planet, which is to say it's a big comet, but kind of a separate criteria. And there are other Kuiper belt objects that are the same size as Pluto and even more massive, slightly, further out in the Kuiper belt, and certainly many that we haven't discovered, or very likely many we haven't discovered. Planets all orbit in the same direction and nearly in the same plane, okay? So besides the exception that I made a big deal about with Venus, the orbit has no exception. There's no planet out there that is orbiting the wrong way, okay? Now the same plane is nearly true. The difference is only up to a couple degrees. So if you consider the sun and maybe an orbit of a planet like Earth, right, seen from the side, well, then there might be an orbit of a planet that is slightly off from that, just a couple degrees off. Maybe we have the orbit of Mars and it's just tilted a little bit, but a small angle of tilt. So the overall effect is still about one plane of orbit. All the planets are essentially on this 2D plane, which is interesting because that's often how the solar system is drawn or represented, and it's pretty close to the truth. Thought question 1, first one for this chapter and lecture. How does the sun's radius compare with the Earth's radius? What's your intuition about the size of the sun compared to Earth? 10 times, 50, 100, or 1,000 times larger? Well, it's 100 times larger, okay? It's not as much of 1,000, although there are some stars that are actually that big, believe it or not, even bigger. But 100 is still incredibly vast, considering that we're saying that's the radius that's 100 times bigger. Because saying that the radius is 100 times bigger is not the same thing as saying that the sun is 100 times bigger. In fact, since both the Earth and the sun are volumes, they are these three-dimensional spheres, to have one dimension that's 100 times bigger means that the volume of the sun is going to be 100 cubed times bigger. Well, 100 cubed is 1,000,000. So it's 1,000,000 times bigger in volume than the volume of Earth. Right? So we could put the volume of Earth in there because it would have gone along with the cube. All right. And then we'll have the volume, actually, it would be outside, right? Because of the radius. So it'd be the volume of the Earth. So then we have the volume of the sun is 1,000,000 times the volume of the Earth. 1,000,000 Earths, if they were able to be melted down and squeezed into all the available space, would fill the sun, and it would take that many, approximately. All right, so here are the planets to scale, which we saw in that other figure, all right, but what we didn't see in the other figures also scaled to the sun, because whenever you scale the planets to the sun, even giant ones like Jupiter, you have to do it in this way, usually where you cut off some of the sun, because it just doesn't fit in the image. You know, we'd have to make, say, Mercury too small to see if we were to see the sun, unless it was a big poster of some sort, okay? Because the sun is just that much bigger. And also, this really highlights the idea of what it looks like to have an object that's 100 times bigger on a radius, right? Like, you know, comparing like, you know, one ball, like a marble or something, to a giant beach ball, and saying that the beach ball has a radius that's 100 times bigger than the marble. It probably would have to be something smaller than a marble compared to a beach ball, because look, right? Look at the comparison. You know, look at that radius of Earth, or even the diameter, 2 times the radius, and think it's just a little tiny thing, right? We'd have to take that many Earths, you know, stacked across to go all the way across the sun, and then we have to fill in another row of Earths, right? And that's just to fill in one slice of the sun. It's a three-dimensional object. That's why it takes so many to fill the space. 1,000,000 is a huge number, 1,000,000 Earths to fill the sun. Now, another interesting thing, you know, we've seen this, you know, back here a couple of figures ago, we saw the zoomed out version of the solar system. I mentioned this with 2 different scales, and, you know, that, okay, we acknowledge, yeah, there's 2 different scales, right? You know, the planets are much magnified relative to their distances, right? And here again, we're seeing the distance between, or the relative size of the planets. But what none of these figures have really driven home is just the vastness between the planets. Well, in other words, how much bigger the distances are compared to the diameters of the planets themselves. It's just so much empty space. You know, you have a giant world like Jupiter, this huge gas giant, but then the expanse of just vacuum between Jupiter and the next giant planet, Saturn, is just unbelievable. So much emptiness with almost nothing in it. Yes, some gas, there's some, some stray asteroids, tiny little particles, but very little. And it helps them to bring home the idea of the scale of the solar system, to see it on the scale of like a park or down a large street, or in this case, comparing with museums in, I believe, Washington. Yeah, so Washington Monument. So famous museums along a particular part of the capital. So if you consider the sun, you can then see like the distance is large. You have to walk many feet to get to the next planet, right? And the planets just are represented in their two scales, so all one scale as these small metal objects, but you have to walk so far to get to the next one. All right, so a huge amount of empty space, very little actual matter in the solar system. it, One way to think about that is you can think that when a gas cloud collapses down and becomes a star, most of the gas does collapse. There's very little that gets left behind. The collapsing process is quite efficient. There's a release of energy, there's gravity pulling everything in, and the few leftovers, the small amount of matter that isn't successfully able to collapse into the protostar and become a star like our own sun, those left behinds are everything that makes the planets and the asteroid belts and the distributions of comets. And so there wasn't that much to start with, so there's almost all emptiness in any given solar system. Okay, so I mentioned before that one big idea is comparing between planets. So in that field of study is called comparative planetology. And we can learn more about a world like ours by studying it in the context of other worlds. It helps us understand things like our magnetic field and why we don't see it on the other terrestrial planets, strong magnetic fields, that is. It helps us understand things like atmospheres and the atmospheres we see. We can maybe arrive at those same rules by just looking at our own planet, but being able to compare allows for so many breakthroughs in science. So we stay focused on the processes common to multiple worlds, of course, all based on most common rules of physics. All right? It's not just a list of individual facts. We need to find the understanding, the common tie between them. Okay? That's why we spent so many chapters, so much time talking about those background rules. And comparing the planets reveals those patterns, okay? The patterns which are the title of the next section and which will be the next video. Those patterns provide insights to help us understand our own planet, certainly, but also help us think about how we could, mine or live on other planets. Okay, so let's do a little review here. This will seem like a list, but do keep in mind that the list is only important in the context of comparison and patterns. So we got the sun, all right? As I said, the sun was really efficient at pulling all the matter in, or the process that created the sun, and it is 99% of the solar system's mass. Everything that forms all the planets is just 0.1%, right? A tenth of 1% of the solar system. And you think, well, then most of that's going to go to the gas giants. They're much bigger than the terrestrial planets. So that means the terrestrial planets are going to be some 100th of 1% of the overall mass of the solar system. There's a tiny little bit. There's a tiny little remnant, a fleck left over from the process that created the sun. All right, now the sun itself is made mostly of hydrogen and helium, as are all stars. This is closely tied in with our understanding of the universe as a whole, and the fact that the Big Bang only made hydrogen and helium, and all the heavier elements have been made inside of the core of stars since then. In other words, at previous generations of stars before our own sun. Okay, the state of matter that hydrogen and helium exists in is a plasma, which is an ionized gas, fully ionized because of the high temperature, and then hot enough in the core to create fusion. And the process of fusion allows for mass to get converted directly into energy, following Einstein's famous equation of E equals mc squared. So that's the sun. There's so much more we can talk about in terms of the physics, the idea of stars like our sun and how it relates to other stars. But here, we're more focused on our own solar system. So we will move on to the first terrestrial planet as we move away from the sun. This one is Mercury, the planet closest to the sun by far. It is also the most metallic planet in the solar system. It has a much thinner rocky layer on top. All the terrestrial planets have layers with more rock on top and more metal in the core. It's completely desolate, all right? It's covered in craters, looks a lot like the moon, right? Although it doesn't have the large maria that the moon has. It has long, tall, steep cliffs. This is a very interesting feature of it, almost like the whole planet cooled at some point and sort of scrunched up as it shrunk, because you think of something cooling and becoming smaller. It is very hot on the surface during the day and very cold at night. That's because it almost completely lacks an atmosphere, and being so close to the sun means that when it is facing the sun, the huge amount of radiative energy, just due to proximity, and all the high energy light, such as UV and X rays, that are not being absorbed in an atmosphere, means that the surface just bakes under the influence of all that sunlight. Because sunlight, sure, mostly visible, but there's a lot of also high energy photons, high energy light coming from the sun, and are all hitting the surface of Mercury. So much so that there's a constant breaking of the surface. The light itself slowly just degrades the surface of Mercury, breaks down that rock, and it creates a thin atmosphere on Mercury, basically made of all those freed molecules. And it actually explains why Mercury is so metallic, or it's a good hypothesis of why Mercury is so metallic, that it's actually just gradually been eaten away by the sunlight over hundreds of millions of years, and the metal core remains. All right. On to Venus, the next planet further from the sun, significantly further from the sun than Mercury. It is almost Earth's twin. It's almost the exact same size and density and volume and everything. However, what's totally different about it is its atmosphere, because it does have a very dominant atmosphere, which Mercury doesn't. So on the one hand, maybe that's Earth-like as well, but its atmosphere could not be more unlike Earth's atmosphere. It is completely dense, cannot be seen through with visible light at all. The only way to see the surface of the planet is to send a lander to the surface of the planet, which is very difficult based on the conditions we'll discuss quite briefly, and looking through the clouds with some long wavelength light like radar. All right. So there are some pretty detailed images of the surface of the planet, but they've all been taken with radar and then artificially colored into what looks like an image. So the surface is completely hidden to visible light. Really extreme conditions on this planet. This atmosphere is all CO2, and it is also all has a huge amount of just vaporized water. There's no liquid water on the surface, and the effect of having this highly CO2 atmosphere plus a significant amount of water in a gaseous phase means that it is a greenhouse to the highest level. It traps almost all infrared radiation, and it's just baking under this dense, thick sheet of an atmosphere. And what it creates on the planet is a no day-night cycle, just a constant baking 470 degrees that doesn't vary. Now, to be fair, the day-night on Venus is itself quite dramatic. It has a day that is almost just as long as its year, because it's rotating on its axis so slowly. So, first of all, they'd be a very long day and a very long night, which you might think would make them quite extreme, where the day would get very warm and the night, where there's just no light for so long, it would cool off. But even having one half of the planet face away from the sun for hundreds of Earth days, hundreds of consecutive Earth days, never allows that side of the planet to cool off, because there's just so much heat trapped in the atmosphere, underneath that dense layer of clouds, underneath all that greenhouse affecting CO2, those gases that re-radiate infrared radiation back down the surface, trapping it in the same way that glass does, hence the name greenhouse. Okay, so that's Venus, the greenhouse planet. Incredibly hot, 470 degrees Celsius melts metal. So just a hell-like planet. So and the heat is so dramatic that it allows lava to flow. There's just constant volcanoes, because it's so easy for magma to break through the surface, because it's just everything's so hot. No life on Venus, no conditions for life. Then onto Earth, of course, it is the opposite, an oasis of life. And Venus maybe could have been, but conditions ended up being quite different. And Earth has gone through, cataclysmic events in the past where life has been disrupted, or the planet has become almost inhospitable for life, based on the fossil record and looking at traces in the minerals and so on, mineral layers. But now things seem to be fine, although we have more greenhouse effects ramping up on our own planet. We have oceans. There are definitely no oceans of water on any of the other terrestrial planets. It's completely unique. We have ice caps on the poles, because we have an axial tilt, so we have some nice differentiation between seasons and poles, making for some interesting phenomenon there. We also have plate tectonics, which is found on no other of the terrestrial planets. So another unique phenomenon, although Venus certainly has an active core, has a molten core, which by the way, Mercury does not. Well, Earth does, but it also has that special feature of plate tectonics. And one of the exceptions, one of the fascinating details of the solar system, we have a really large moon. Our moon is just surprisingly large. There's no other terrestrial planet that has a moon anywhere near this large. The only terrestrial planet that has any moon at all is Mars, with two small moons, which are trapped asteroids, as far as models and theories suspect, and that's basically what they look like. There's lumpy rocks that are stable orbits around Mars. But our moon is amazing. It's huge. And there's been many interesting theories about why that is, including that it was created, most likely, with a giant impact in the first 500 million years or so of Earth's history. Well, on to the last of the terrestrial planets. So this is the furthest one from the sun. Obviously, Earth was the third. So Mars is further out, which means it's colder. It's at the very edge of where we start to have conditions that would allow for, basically water to just freeze in space itself. So Mars is not further enough out where water molecules are freezing between planets. So in other words, water, if you were to have water out in space anywhere at the edge of, anywhere in the distance from the sun that's the same as Mars orbit from the sun, water in space would remain in a gaseous phase. And you might think, well, water would always remain in the gaseous phase in space because isn't space a vacuum? Well, it's a near vacuum, right? There is some pressure from other molecules. There's some tiny amount of matter that exists between planets. And once you get further enough from the sun, you get to a point where if you did take H2O and you put it out into space, it would actually freeze because there's not enough radiative energy from the sun anymore. And that's where water starts to freeze in space. And that's where you can have the conditions that allow for gas giants to form. But all of that is a story we'll get into in some more detail. But I just bring that up because Mars is at that point where terrestrial planets can still form. Okay, so it's right at the edge of that point. Okay. It looks kind of Earth-like. We see the rovers driving around on Mars, and you have in the news. There's a horizon often. There's some almost small amount of clouds. It has dust storms. So you might think, oh, it's a little planet. Can we move there and start building bases on Mars? Well, it has a tiny bit of atmosphere, but very, very little. So much so that the pressure is much, much lower. Right? So very low pressure because the atmosphere is so thin. So you really can't go there without a spacesuit. It would feel like being in outer space. You would suffocate, all right? And even if you didn't suffocate because of the near vacuum, the only gas that exists in its thin atmosphere is CO2, all right? So there's a thin atmosphere of CO2, whereas of course Venus was the opposite, an incredibly dense atmosphere dominated by CO2. So both the planets have the same molecule, but doing very different things. On Mars, that there is enough of an atmosphere that recently NASA has been flying a helicopter around Mars. So it's not a vacuum, but the key to that helicopter is it's quite light and it spins its blades at such a fast rate it's able to generate lift. But again, being on the surface, you wouldn't notice wind or anything significantly, except during those very strong dust storms where that thin atmosphere is able to actually pick up enough force, surprisingly. But it has some interesting dynamics there, probably between energy and thin atmospheres. But regardless, it's smaller than Earth. All right. It does have some giant volcanoes that are still active, so it does have some active heat still inside of the planet. It does not have a magnetic field, by the way, unlike Earth. All right. It has a huge canyon system that really dominates, a really amazing canyon system, 100 times larger, or more than 100 times larger than the Grand Canyon here on Earth. And it has polar caps, actually has some water frozen in the caps, but no axial tilt. And there's really compelling evidence. So basically what you could say is clear evidence that water flowed on Mars. It really doesn't look like anything other than lots and lots of evidence of former flowing of water. So there was at some point a thick enough atmosphere to hold in enough heat to support liquid water. Because with Mars's current incredibly thin atmosphere, there's no way that water would not just freeze. There's just not enough heat. There's not enough greenhouse effect, which is good in small amounts, to hold in the heat to allow for liquid water. But at some point there was, maybe 3.5 billion years ago or 3 billion years ago, Mars absolutely would have had oceans, probably weather. Now, I'm not saying it would have had an atmosphere favorable to life, because there would have had to been the same cycle of changing atmosphere that our own planet experienced, where life evolved to take in CO2 and create oxygen as a byproduct, and then later different forms of life evolved to take advantage of that byproduct and tied in a cycle of CO2, production, oxygen production, consumption, and so on, right? But that's the only way we have free oxygen in our atmosphere, because of life. And as far as we know, free oxygen does not occur in any atmosphere without life. And so it would still have been, some billions of years ago, an atmosphere dominated by CO2, but a planet that would be much warmer and have liquid water. So, that seems like at least more to work with. But unfortunately, over time, Mars apparently lost its atmosphere and now is much colder and less hospitable. But it's still our best bet of somewhere we could live other than Earth. But we'd either have to live in spacesuits or maybe terraform the planet, maybe build an atmosphere. But that's not something you can do in just a few years. So, we're done with the terrestrial planets. Let's go out into the deep solar system and go to the biggest planet in the solar system, the gas giant closest to the sun, and that's Jupiter. It's much further from the sun than the planets. We talked about it. It's a huge gap. By the way, we jumped over the asteroid belt. Now, Jupiter is made of the same molecules, the same atoms as the sun, primarily hydrogen and helium. We're going to see that's actually true of all the gas giants, all right? There's no solid surface. That's why we call these gas giants. They're gas planets. Another term for them is Jovian planets. They don't have a surface. They have clouds, and if you dove down in the clouds, the clouds get denser and denser as the clouds above create, more and more pressure. And then you essentially then would just get to the point where that pressure gets great enough that the clouds gradually transition into a liquid due to all the pressure above, and then you're in essentially an ocean at some point with no clear transition between them. Right? There's no surface of the ocean. There's just denser and denser clouds as you get deeper in. Right? At least that's our understanding. That's our best models. We haven't gone in. We've used some compelling techniques to view into the clouds to some extent with with the right imaging, but we're not we don't know for sure what's down there. Interestingly, also with planets like Jupiter and Saturn, which we'll talk about in just a moment, they're such giant worlds that even at the top of their clouds, like if you were to have like be on a space probe or something, or fly by and have some sort of lander that would be that would take you down in a helicopter into the upper clouds of Jupiter, well, that probably would not be good to send people on such a mission, because the gravity just in the clouds is 20 times greater than the gravity on Earth, because the planet's so massive that even though it's larger, and even though you're way up in the cloud layer, you would feel 20 times heavier than you do on Earth. So essentially you would be crushed under your own weight. So not great conditions, right? That no people could ever go to Jupiter. But we could potentially send robots of some sort to Jupiter, or a planet like Jupiter, one of the other gas giants. Now, in terms of things being more massive, Jupiter's 300 times more massive. So not a million times more massive like the sun, but still quite a bit more so. All right. And Jupiter is like a little solar system onto itself, in the sense that it's has a huge amount of moons, and that's also true of Saturn. So many moons, such a dynamic system of moons, just because of its large gravity. It's got enough gravity to create very compelling orbital dynamics. The thing is that what isn't like at all like a solar system is it's not a star. It doesn't have fusion. It's not radiating its own energy, and it's not a failed star either. It's nowhere near the mass necessary to be a star. All right, Jupiter's not a brown dwarf. It's not a failed star. It's just a normal sized gas giant. Right, on the large side, yes, but definitely just a gas giant. All right. So Jupiter's moons can be as interesting as the planet themselves, sometimes almost more so. The moons are amazing, and this is true with the other gas giants too. The Galilean moons, for example, so named because they were viewed by Galileo or first documented by him. They're large. Io is a very large moon of active volcanoes. So it's like it's a volcanic it's almost like a terrestrial planet into itself, right? Europa has subsurface oceans, which we basically have, I would say, have confirmed their existence. We can see their effects and the release of energy through cracks on a mini kilometer thick sheet of ice on top of those oceans. The oceans are thought to have more liquid water than on Earth. So here's liquid water out in the solar system, right? We're not finding it on Mars, we're not finding it on Venus, but apparently it's out there. It's just on the moons of the gas giants, all right? Ganymede is the largest moon in the solar system, so large it's larger than Mercury. Callisto is less interesting, but still quite large and is in a mix of ice and rock, all right? Moving on to the next of the Jovian planets, so further away from the sun. Of course, Saturn is famous for its spectacular rings. Its composition is really similar to Jupiter's. It's hydrogen and helium. Interestingly, it's also significantly less dense than Jupiter. I mean, really much less dense. It's the least dense planet in the solar system and the only planet in the solar system with a density less than water. Now, like Jupiter, it has a ton of moons, including Titan, which is the only really planet, or not planet, but only world, which a world is a term that we use when we want to group together moons and planets because we want to talk about things like this. So Titan is the only world in the solar system other than, well, Earth and Venus that has a large atmosphere. All right. And it's a terrestrial world. So it's got a surface, and it's got a very dense, significant atmosphere and not a hellish one like Venus, but not a hospitable one like Earth. Because it is so far from the sun, it's actually a frozen methane atmosphere that has clouds and it storms, but on an incredibly slow time scale because it's so much colder, there's so much less sunlight, so much less heat coming from the sun, so far from the sun, that basically there'd be like a weather pattern. What scientists think that methane builds up and then rains down methane and ammonia every 10 or so Earth years in a huge torrential rainstorm. And there's actually there's erosion, there's lakes of methane, all on the surface of this cold world, but a familiar kind of idea with clouds and rain and so on, but not water, instead ammonia and methane. All right. So the rings of Saturn, by the way, are not solid. They're actually a very loose mix of largely water ice that's just highly reflective, making them look solid, but it's a very actually low density, mostly tiny little pieces of water ice and a few large pieces of water ice that are meters or hundreds of meters across. All right. On to the next gas giant. All right, this is Uranus. Now, Uranus is the first of the two gas giants, which are sometimes called the ice giants, because they're much colder than Jupiter and Saturn, being so much further from the sun, and Uranus in particular is cold, and because they start to have some other compounds, other molecules that are showing up than just hydrogen and helium, and that can be owed to the different thermal conditions. If these colder planets allow for other compounds to form with a greater probability, including methane and ammonia, the same compounds that we saw that dominate the weather patterns and the thick atmosphere on Titan. All right, so we're kind of out this common theme here. All right, now Uranus is famous for its extreme axial tilt. It also has a faint ring, by the way, not as dramatic as Saturn, but the most noticeable of the faint rings, because, by the way, all the gas giants have rings. All right, but for example, Jupiter's is so faint you can't see it. You can only pick it up in the infrared. And it also has many moons and rings, all right? Not as huge a system as Jupiter and Saturn's systems of moons, because, by the way, Jupiter has something like 70 moons, same number for Saturn, but Uranus still has dozens of moons, and it has a large amount of gravity. It's still a huge world, but it's also significantly smaller. We're basically cutting, the volume by half when we go from a planet like Saturn to a planet like Uranus. But almost identical in size and volume is the next planet, the very last planet of the solar system, Neptune. All right. Now, Neptune's a lot like Uranus, but it doesn't have the axial tilt, and it's actually warmer than Uranus, despite being much further away. And it has interesting moons, so huge, moon system, including a very mysterious moon, Triton, which orbits the wrong way. Now, I said no planet orbits the wrong way around the solar system. There is one planet that rotates around its own axis the wrong way, Venus, of course, right? I made a big deal about that. But Triton is the only moon that orbits the wrong way, at least the only large moon. There are actually many small moons that do because they're all captured asteroids. But Triton is a large moon, almost like that's comparable in size to a moon like Ganymede or Io, the famous, Galilean moons. But Triton, or it's the size of Pluto, really, but Triton orbits the wrong way, which means it's a captured dwarf planet. So not only do we see that these gas giants can capture asteroids, or even terrestrial planets like Mars can capture asteroids and turn them into moons, they can even capture dwarf planets. All right, in all that history and time. Talking about dwarf planets, those that haven't been captured and demoted to moons, we have Pluto, Eris, and more, right? What makes them dwarf planets? They're much smaller, so it's a big step down in size, all right? And I know Mercury is kind of a middle ground there, but it's not a dwarf planet. It clearly qualifies as a planet with official criteria. All right. Most dwarf planets, with the exception of Ceres, are icy comet-like. All right. Eris, by the way, is a Kuiper Belt object, so it is like Pluto. Another famous one is Makemake, which is out also further in the Kuiper Belt. All right. And Pluto's main moon, Charon, is almost the same size as it, as we can see here. Talk about having a large moon. In fact, it's more like a two-planetary system. So it's like the two dwarf planets here are orbiting each other because they actually orbit their shared center of mass, which is their balance point between them. All right, here's a summary of a ton of information. A lot of the stuff we talked about, all numerically represented: average distance from the sun, average equatorial radius, so the size of the world, the mass of the world as multiples of Earth's mass, the density. This is a good one to compare to water. There's that density for Saturn, the only one that's lower than 1. The orbital period, so that's comparing it to number of Earth days, right? So we can see, for example, or actually in Earth years, excuse me, only days for the really short ones like Mercury. Then the rotation period, this is like the planet's day, how long it takes to rotate on its own axis. Notice that really the only long ones are planets like Venus and Mercury, interestingly, the terrestrial worlds. Once we get up to the rotational period of the gas giants, which you might think due to their huge size would be slow, they actually all spin really quickly. And that's kind of a conservation of angular momentum argument, that as they've shrunk down in size, collected in so much matter, they're really spinning fast. The average surface temperature, this is going to be affected by atmospheres for the terrestrial planets, and then for the further planets, the gas giants, just because they're so far, we're going to have much lower temperatures. The composition, which we've talked about, right? Terrestrial versus Jovian, including what molecules in the case of the Jovian, known moons, all right? Here's those large numbers I was talking about, all right? And then whether there's rings or not. So a bunch of comparative values, all the planets summarized in one table. Pretty neat. All right, so let's do our thought question as we get near the end of this section. What process created the elements from which the terrestrial planets were made? I mentioned this earlier. What process? Where did those elements come from? The heavier elements, the things that make rocks and metal. All right, nuclear fusion. Every bit of calcium to carbon to certainly things like gold and uranium that we find on our planet, all those elements, everything that's not hydrogen and helium, all came from the core of a star that at some point blew up, spread that matter through space, and then that matter coalesced into our planet as a tiny little leftover of a solar system. So what have we learned in this section? Well, we've answered the question, what does the solar system look like, right? We understood its vast size, the relative size between planets, the huge emptiness of it, the fact that it's a plane. We've also answered the question, what can we learn by comparing the planets to one another, right? We learned that we can compare them through size, through composition, through temperature, through axial tilt, all kinds of things. And that there's big patterns, there's connections between them, right? And then this can help us understand the rules that govern our own world, make us anticipate things, make us ask the right questions in order to collect the right data for our own planet. Well, in our next video, we'll discuss patterns in the solar system. Well, thank you so much for watching this video. I hope it has been interesting and informative.